Hello, my name is Ulla Blumenschein.
I'm Dr. Linda Cremonesi.
My name is Dr. Alison Elliott.
My name is Dr. Tessa Baker.
I'm a senior lecturer in the particle physics group at the School of Physics and Astronomy.
I'm a UKRI Future Leaders Fellow and lecturer in particle physics.
I'm a postdoctoral research associate.
I'm a Royal Society University Research Fellow and senior lecturer working in the School of Physics and Astronomy at Queen Mary University of London. And in particular, I'm a cosmologist in terms of my research. So I work in the astronomy unit.
When I was a kid, I wanted to be an astronaut. I think many kids want to be astronauts. And later, when I grew up, I realized that the chances to actually travel to the space station are quite small. So I changed my career path towards astronomer, and then later it became astrophysics. And then even later I realized that if I actually wanted to investigate the origin of the universe, I have to build colliders and have particles interact at very high energy densities, because this would simulate the early conditions of the universe. And so I ended up in particle physics.
What led me to a career in physics? I was always very interested in nature and in the universe, and I was always very curious about how things worked, and that's why I was always very attracted by physics. And throughout my career, I have been working in particle physics, which study the building blocks of matter and everything around us.
I think I came to a career in physics because I loved looking at the stars when I was a kid. I got my first telescope at 15, and I remember looking through it for the first time at Saturn's rings and seeing the moons of Jupiter. I was also pretty good at mathematics, so I decided to study physics when I went to university. It was after my first course in quantum mechanics, though, when I learned about the names of the quarks, that I was really hooked. Particle physics was going to be my thing.
So I chose to do a career in physics because it seemed to be the way to tackle some of the most exciting questions in the universe, it seemed to me. So when I was in secondary school, I used to get the train to school every day, and I read a lot of popular science magazines and a lot of popular science books on the train journey that got me really excited in things like the Big Bang, cosmology, other bits of astrophysics, quantum physics. And it seemed like there was all this fascinating stuff out there. And I realized that if I started making the right choices now, as a school student, I could actually study those things for a career, which to me just seemed absolutely mind-blowingly exciting, and that's how I ended up here.
What am I doing? My group and I'm a member of an experiment at the Large Hadron Collider in Geneva at the CERN laboratory, and we're often traveling there. My students are traveling there to work together with the physicists, but we can also work from here. We get the data, and we can analyze the data from here. I'm searching for new particles, for new forces, new physics, but I'm also measuring processes which could mimic new particles, because you have to understand them very well. Otherwise, you take something for a new particle, you publish a paper, and then it turns out it is actually a standard process which is well known. That would be pretty embarrassing. So I'm working in both directions. So far we have only found the Higgs boson, which was of course very great. It was a great adventure, but now we are looking beyond the Higgs boson and see what we can find.
My current research at Queen Mary is revolving around neutrinos. Neutrinos are the smallest particles that our brain can think of, and they're pretty special. They're everywhere. Every second we've got trillions of neutrinos going through our body, and they very, very rarely interact. But because of a weird behavior that we can see in neutrinos, this behavior is called neutrino oscillations. Neutrinos can change flavor when they propagate. They can tell us something about the origin of the universe. So that's what I'm trying to do. I'm trying to find out why the universe evolved to be dominated by matter rather than antimatter through the study of neutrino oscillations.
I'm currently working in the Particle Physics Research Center at Queen Mary's School of Physics and Astronomy. I'm searching for dark matter. I look for dark matter by using the ATLAS detector to study what comes out of smashing protons together at the Large Hadron Collider in Switzerland. Dark matter might be a new kind of particle, and I'm looking through billions and billions of events that we recorded to try to find evidence that there's some connection to dark matter from those events.
So right now, I am researching the laws of gravity that govern our universe. So gravity is one of the most important forces of nature. It's the thing that drives the evolution of our universe from the Big Bang to the universe we see today that's full of stars and planets. But there are lots of things we don't know about gravity, lots of things that don't quite make sense. And in particular, there's a puzzle going on with the expansion rate of the universe. So we can measure how fast the universe is expanding, and it seems to be doing that far too quickly, expanding far too quickly from what we would predict using our standard laws of gravity, which are, of course, come from Einstein's theory of general relativity. So I work on a whole bunch of things trying to figure out if there could be extensions or things we missed in Einstein's theory. How would we work those out mathematically? And also how would we test those ideas with astronomical observations, so things we can actually see with telescopes or with the detection of gravitational waves.